Finding a domain, before I write down my function that I'd started writing before, let's talk about what domain mean. And if you think back to Algebra 1, the domain of a function is the set of all x values. Now, for many things, your domain is all real numbers. So for example, f of x equals 3x minus 1. We've dealt with this a lot in Algebra 1. This is a line. It has a slope of 3 and a y-intercept of -1. And if you look at what that graph looks like, okay, if I was just to make a quick sketch, you'd have a y-intercept of -1, and then it would go up 1, 2, 3 over 1, and you draw this. The thing is, this arrow never stops extending to the right-hand side. It never stops extending to the left-hand side. So, we include every single x value that there is. And so the way we would say the domain here is the domain is all real numbers. And for polynomial functions, your domain is going to be all real numbers. But there are cases where we're going to end up restricting the domain, and what we've started talking about now are these rational exponents. And if that's ever the case, the domain may have to be restricted. So for example, let's consider the case of f of x is equal to x to the 1/2 power. Well, we just learned that x to the 1/2 power is really the square root of x. And so what we want to do is we want to consider what numbers can I substitute for x. Can I substitute anything I want for x? Like if I substitute a positive number, so for example, let's say the square root of 9. Well, I know who the square root of 9 is. That's 3. That's fantastic. And let's say we do the square root of 4. And I know that the square root of 4 is 2, and we're wonderful. Okay, and what about something in between, like not a perfect square, square root of 5? Well, I don't know what the square root of 5 is off the top of my head, but I know that it falls somewhere in between 2 and 3. And we could substitute that into a calculator, and it will spit out a number for you. And again, I don't know what it is off the top of my head, but it's somewhere in between 2 and 3. And then what about 0? Can we do square root of 0? Yeah, we can, because 0 squared is equal to 0, so the square root of 0 is 0. But then you get into things like, what about the square root of -1? And we said when you do square roots of -1, we're getting a non-real answer. And so if that's the case, then we can't use negative numbers in our domain. We can't substitute a negative number into the square root function and get a real answer. Same for anything, square root of -3, square root of -4, any of those are going to be non-real answers. Okay? So in this case, we have to restrict our domain. And the way we do that is we say, okay, well, the domain is all real numbers, but we put a little restriction on it. And we say it has to be greater than or equal to 0. Okay, because those will be all your positive numbers plus 0. And this is a lot to write, so the way mathematicians have shortened that is we say that x is greater than or equal to 0. And that means the same thing. All real numbers greater than or equal to 0. And we use x because we're talking about domain, which is, of course, the set of all x values. But, that's for x to the 1/2 power. Recall that if your index is even, so for example, let's say we did f of x is equal to x raised to the 1/4 power. Well, we're going to have the same issue. Okay, the fourth root of, remember, x to the 1/4 is the fourth root. If you substitute a negative number and you take the fourth root of it, well, that's going to give you a non-real answer. And so again, this domain is going to be x greater than or equal to 0. But if we consider f of x is equal to x to the 1/3 power, well, in this case, you can substitute anything in there because this is the cubed root of x. And the cubed root of x, like if you take the cube root of 8, Well, 2 times 2 times 2 is 8, so the cube root of 8 is 2. The cube root of negative 8, well, negative 2 times negative 2 times negative 2 is negative 8. So this is equal to negative 2. We do get an answer there. So the domain, in this case, does not need to be restricted. Domain is all real numbers. So again, it's when you have an even index, fourth root, the square root. If you did the sixth root, that's when the domain is going to have to be restricted to x greater than or equal to 0. There's one more case we need to consider here, and that's if you have a denominator with a variable in it. So for example, 1 over x. Okay. Well, what happens if we substitute well, we can substitute a positive number in here, like 1/4, you know, f of 4 is equal to 1/4, and we're okay with that. And we can do a negative number as well. That would just be 1 over negative 3, which is negative 1/3, and we're good with that as well. But what happens when we try and substitute 0? Okay, well, that would be 1 over 0, and Scooby, we can't divide by 0. So you can do all the positive numbers, you can do all the negative numbers. So the domain, we say, is all real numbers except x equals 0. And so what's going to happen is you're going to be given things like f of x equals, we just started learning about negative exponents. And so you have x to the negative first power. And you have to recognize, well, that is 1 over x. So the domain is going to be all real numbers except x equals 0. And then finally, they'll give you things like f of x is equal to, for example, x plus 1 raised to the negative first power. We'll recall that this is the same thing as 1 over x plus 1 raised to the positive first power, which is really just 1 over x plus 1. And so you have to think, when does your denominator equal 0? Well, take that denominator, solve when you set it equals for 0, and then you know that, hey, this is the number that makes the denominator 0. So the domain of this is all real numbers except x equals negative 1. Okay, because again, when you solve for that, x plus 1 equals 0, when you subtract 1 from each side, x is equal to negative 1. You substitute negative 1 into this function, you're going to have negative 1 plus 1, that's 1 over 0, and that's a big no-no. So, just as a little bit, kind of as a sum up here, okay, typically, you know, with algebraic functions, polynomials, and so we're talking about like x squared, x to the third power, x to the fourth power, anything like that. The domain, and that's domain, is all real numbers. But there are cases where you have to restrict. Okay, so we'll put restrict the domain when. Okay, and there's two cases where we're going to restrict to the domain: a radical with an even index. And so again, an example of that would be the square root of x, the fourth root of x, the sixth root of x, anything like this. You're going to need to restrict your domain. Okay, and then finally, variable in the denominator. So, for example, 1 over x, or remember that can be written as x to the negative first power, or 1 over x minus 3, which could also be written as x minus 3 to the negative first power. Anytime you're going to have a variable in the denominator, you're going to have to restrict your domain. we're adding and subtracting functions. We're given f of x equals 2x to the 1/2 power and g of x is equal to negative 6x to the 1/2 power. First thing we want to find is letter A, f of x plus g of x, and we want to state the domain. Well, of course, we look up here to see who f is. F is 2x to the 1/2 power. G of x is negative 6x to the 1/2 power. And so we have 2x to the 1/2 plus negative 6x to the 1/2, and that is negative 4x to the 1/2. Now the domain of a function, really we'd like a domain of the function to be all real numbers. You can substitute any value for x, but there's some cases where we have to restrict the domain. And so in this case, think about what x to the 1/2 means. X to the 1/2 power, recall from an earlier section, is really the square root of x. Okay? And if you think about numbers you can substitute into x, okay, x has to be greater than or equal to 0. If you put any numbers that are negative into the square root of x, you'll get a non-real answer, like the square root of negative 4 is 2i, the square root of negative 1 is 1i. But you can take the square root of 0, you can take the square root of 1, 2, 3, 4, 5, any number greater than or equal to 0. So the domain of this function, we say, is x greater than or equal to 0. For letter B, we have f of x minus g of x. And so we'll take our f of x, that's 2x to the 1/2 power. And then we're going to subtract g of x, which is negative 6x to the 1/2 power. And so 2x to the 1/2 power minus negative 6, well remember, subtract a negative is like adding a positive. And so you have 2 plus 6x to the 1/2 power, and that makes 8x to the 1/2. Again, remember that x to the 1/2 is the same thing as the square root of x, so we can't substitute any negative numbers for x. And so the domain here, meaning what can we substitute for x? X has to be greater than or equal to 0. And we'll box this up as well. Talk about multiplying and dividing functions. We're going to let f of x equal 3 times x and g of x equal x to the 1/4 power. And so we want to find the product for letter A. We want to know who is f of x times g of x. And then we want to state the domain. So f of x, we look, it's 3x to the 1st power times g of x, which is just x to the 1/4 power. So we have 3 times 1, which is 3. Then this is x times x to the 1/4. And remember what we do here, this is x to the 1st power, so our rule is to add the exponents together. So that's 3x to the 1 plus 1 over 4. And so that's 3x to the 5/4 power. Now recall, you have to look at your original equations up here. X to the 1/4 is the same thing as the 4th root of x. That is x to the 1/4 power. And because our index is even, just like with the square root, you can't substitute negative numbers for x there because, for example, the square root of negative 4, that's equal to 2i. So same deal with the 4th root of x. We can't substitute negative numbers for x. So the domain of this function is going to be all real numbers greater than or equal to 0. All x greater than or equal to 0. And for the quotient, we're going to do f of x over g of x. Well, in this case, f of x is 3x. G of x is x to the 1/4. And then if you can simplify, you should. So we have 3x over x to the 1/4. what I see is an x on top and an x on bottom. Now, if you recall your rule, you're going to subtract your exponents. So the 3 is just going to stay. And then since we have more x on top, because 1 is bigger than 1/4, my x answer will go on top. And we're going to do 1 minus a fourth. And then 1 will be left over on the denominator. Okay, so this will be 3x. 1 minus a quarter is 3/4. And then again, because we started with an x to the 1/4 power, your domain is going to be all x. But in this case, we can only put greater than 0. We can't put greater than or equal to 0. And the reason that is that if you come back to your original function, which was way over here, okay, if you substitute 0 for x, okay, you're going to get 3 times 0 all over 0 to the 1/4. And 0 to the 1/4 is still 0. So you have 3 times 0 over 0. And ruh-roh Scooby, we cannot divide by 0. And so our domain now is no longer just going to be, before when you had a 4th root of x, our domain was x greater than or equal to 0, but we can't equal 0 in this case because, again, if you substitute 0 here, you're dividing by 0, and that's against the law of mathematics. So our domain in this case is x greater than 0. Function composition is a little bit different. It's another operation that we can do, but it's not like addition, multiplication, subtraction, division. You're kind of substituting one equation into the other. So, for example, before we do these right here, let's kind of scroll down a little bit. And so if I had, let's say, f of, 4, you would tell me, okay, go look at your f function up here, and you're going to substitute 4 for x. And so that would be 3 times 4 to the negative first power, and you could go on and figure out what that was. And if I said, who is f of 5, you would tell me, okay, well, up here you're going to look at who f is, and that's 3. And then you're going to substitute 5 for x, and you would go on and figure out who that is. But then if I said, well, okay, who is f of a tree, you'd say, okay, well, go up and look at your functions. F is 3 times x to the negative first, so you'd substitute a tree into your x, and you'd be happy. And then if I said, okay, well, who is f of a box, this is our last one, I promise, you'd say, okay, well, you'd go and you'd substitute a box into x. But what happens if I wrote on that box g of x? Well, that means over here in this box, you'd also have g of x. And that's what function composition is doing. It's taking the g function here, and you're substituting it into the f. So whatever g is, in this case, and I see g is 2x minus 1, you're going to substitute that into that x. So f of g of x is equal to 3. Then here's the input, and what we're substituting is 2x minus 1, and that's raised to the negative first power. And so you'll rewrite this. Remember, we don't like to leave negative exponents. That's 3 over this whole piece here is going to get brought down as 2x minus 1. And you could put parentheses in a positive first power like this, but you don't have to have that positive first power. Now for letter B, we have g of f of x. And so what that's saying is to take f, in this case, and put it into g. So we're going to substitute that into g. So we'll have 2 times 3x to the negative first power, and then minus 1. And so we'll multiply here. 2 times 3 is 6. X to the negative first minus 1. And once again, we don't like to leave negative exponents. So that's 6 over x minus 1. Finally, we have f of x. And what that's telling me to do is to take f and then kind of substitute it into itself. So here's the outer f right here, and I put parentheses where the x would be, and then I substitute f into that x there, so we'll put another 3x to the negative first. Now when doing this, remember, you want to clear your parentheses, so we have 3, which just kind of comes on down, and then this 3 needs a power of negative 1, So we'll put a times 3 to the negative first, and then this x to the negative first, or this x to the negative first also gets a power of -1. And recall our exponent rules. Right there, we're going to multiply. So we have 3 times 3 to the negative first times x to the positive first, because -1 times -1 is +1. And then there's a couple different ways you could go about this. I see the same base, so I know I can add my exponents together. So that's 3 to the 0 power times x to the first power. And I know that 3 to the 0 power is 1, so that's 1 times x, which is just x. So a clothing store advertises it as having a 25% off sale. For one day only, the store advertises an additional savings of 10%. And so we want to use composition of functions to find our total percent discount. We're going to use it to represent this sale. So we kind of need a function for the 25% sale, and we need a function for the 10% sale. First we need to define our variables, and we're going to let x represent the price of whatever item we're buying here. And so the way we do a 25% sale is you take the full price of the item, which we said was x. Maybe x is $100, maybe x is $1,000, maybe x is 20 bucks. We don't know, but x is the full price, and then you take away 25% of that sales price. So we're going to subtract, because that's take away in math, 25% of the sales price. So 25% as a decimal is 0.25, and then of the sales price, meaning times the sales price there. So x minus 0.25x is the amount you're going to pay, full price minus 25% of the price. And we're going to let this function be f of x. So we'll call g of x the 10% sale, and that means that you're going to take the full price of the item, and then you're going to take away 10%. Now 10% as a decimal is of course 0.10. 10% of the sales price, not just 0.10, not just be 10 cents, but 0.10 of x, that's 10% of x. Now looking at these two here, I see x minus 0.25x, and these are like terms. They're both x to the first power. So you have 1x minus a quarter x, 1x minus 0.25x. Really, f of x can be rewritten as 0.75 of x. This also tells me that you're only going to be paying 75% of whatever the sales price is, which makes sense if it's 25% off. And then over here we have like terms as well. G of x is 1x minus 0.1x, and so that makes 0.9x. And this tells me that I'm only paying 90% of the original price. And that makes sense. If it's a 10% sale, you're paying 10% less than 100%, which is 90%. So on one day, what we're going to do is we are going to do some function composition. So we have our sales price of 25%, and then for one day only, we have a 10% sale. So we're doing f of g of x. And so that, of course, will be 0.75. Then I have my input, and into that I'll put g of x, which is 0.9x. And so we do 0.75 times 0.9, and that is equal to 0.675x. So f of g of x, f composed with g of x, is equal to 0.675x when you multiply these two numbers together. So this tells me a couple things. First of all, this will allow me to find the price of any item I purchase if I know the original sales price. It also tells me that really all I'm paying for is about 67.5% of whatever the sales price is, which is a pretty good deal. So if I want to know what is the price, or the sales price I should say, of a $40 shirt, we're going to do f of g of 40. And so here's my f of g of x function. And so I'll substitute 40 for x. And that makes 27 when you multiply those two numbers together. So the price of a $40 shirt is $27. I should say the sales price